This is still section 5.3, part 2. So the next problem is we're asked to take the function f of x, which is sine of x, show that it is not one-to-one. So to show that, kind of an algebraic showing of that, just think of two numbers that you could take the sine of and get the same answer. Well, an easy one, there are lots of pairs of these, by the way, but sine of 0 and sine of pi are both 0. So that implies that f is not one-to-one. Then we're supposed to show that negative pi over 2 to pi over 2 is the largest interval centered at the origin when f is strictly monotonic. So I'm going to pretend like they didn't tell me and give away all that information. And I'm going to graph the entire graph because they kind of gave everything away just there, which is, I suppose, fine. And the directions may actually give that away for you. Like this. It's possible. But anyway, so if we were to graph the sine function, of course, sine of 0 is 0. Sine of pi over 2 is 1, 0, negative 1, 0. Going this way, negative 1, 0, 1, etc. Of course, it goes on forever. And obviously, it doesn't pass the horizontal line test, as sine of 0 and sine of pi both being 0 attests to that fact. We need to keep all of the range of this function. So the range is negative 1 to 1 inclusive. So we have to keep all of that. If it's periodic, we want to stay as close to 0 as we can. So one interval that could be used would be, for example, pi over 2. I'm just drawing a little bit above so you can see, to 3 pi over 2. Keeps everything from 1 down to negative 1, so that's a possibility. I could keep from negative 3 pi over 2 to negative pi over 2. That would keep it all. But neither one of those is any closer to 0 than the one that it actually has 0 right in the middle of its interval from negative pi over 2 to pi over 2. So when it's periodic, you want to stay as close to 0 as possible, which is this one. This time, the third condition doesn't have to be addressed because we've got both positive and negative x's, and we can't just get rid of one or the other. So from negative pi over 2 to pi over 2 is going to be our restriction on the domain to make it 1 to 1. Okay. Now, we do need to kind of talk a little bit about more of this. Is it strictly monotonic? We've got now 1 to 1, which is what that domain restriction did. Now, to show that it's monotonic, the derivative of sine of x is cosine of x. Find out when that's equal to 0, or when the first derivative doesn't exist, which never happens. You can take the cosine of any real number. And cosine of x is equal to 0 at plus multiples of pi. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2, negative 3 pi over 2, etc., etc. And so if I did a number line analysis, let's go from like negative pi over 2 and pi over 2 and 3 pi over 2, just to name a few intervals for my number line analysis. Pi over 2, cosine of, let's say, 0 is positive 1, so that's positive. From pi over 2 to 3 pi over 2, let's use pi. Cosine of pi is negative 1, so that's negative. But at any rate, what we found out from our number line analysis is that from negative pi over 2 to pi over 2, the function is strictly increasing. With our domain restriction, negative pi over 2 to pi over 2, it is monotonic on that interval. So we now know that we can get an inverse for sine. And if we were to pick any larger range from other than negative pi over 2 to pi over 2, it would start decreasing. And so that is the largest interval that we can use, is negative pi over 2 to pi over 2. So, and no, it didn't say to do this, but I'd like to do this as an exercise in precalculus. So we start with y equals sine of x, that's our original function. The inverse will be x equals sine of y. Then to get rid of the sine, we're going to take the sine inverse of both sides, also known as the arcsine, both sides. And at least on the interval from negative pi over 2 to pi over 2, the sine inverse of sine of y will definitely give you back y. And so y equals sine inverse of x. So therefore, f inverse of x is called sine inverse of x, or arcsine of x. I'll actually write that here. I don't tend to use arcsine because it's more writing and I'm kind of lazy. So I'll use sine inverse all the time. And one thing you need to notice is that its domain is the range of the original function, negative 1 to 1, and its range is the domain that we restricted to, negative pi over 2 to pi over 2, and its graph. And with trig functions, it's customary, as you saw up above and to the left, that we mark the x-axis by intervals of pi over 2 and the y-axis by intervals of 1. But because we're switching everything that has to do with x and y, I'm going to make the x-axis numbered by 1s and the y-axis by pi over 2. Makes our graphs easier and cleaner looking. And so this inverse function and again, the easiest way to start graphing this is to find a few points and switch the order pairs. So negative pi over 2, negative 1 goes to negative 1, negative pi over 2. 0, 0 goes to 0, 0. And pi over 2, 1 goes to 1 pi over 2. And then I graph this, thinking of its reflection over the line y equals x, and it becomes that graph. So that's the graph of our inverse function, like that. Okay, so that's a little bit beyond what the question asked, but I thought that could not hurt to talk about, that problem in its entirety. All right. So the next two theorems discuss the derivative of an inverse function. First, theorem 5.8, continuity and differentiability of inverse functions. Let f be a function whose domain is an interval I, like in this last one, negative pi over 2 to pi over 2. If f has an inverse function, then the following statements are true. If f is continuous on its domain, then f inverse will also be continuous on its domain. If f is increasing on its domain, then f inverse is increasing on its domain as well. If f is decreasing on its domain, then its inverse will also decrease on its domain. If f is differentiable on an interval containing c and f prime of c is not equal to 0, then f inverse function will be differentiable at the output f of c. Then theorem 5.9, the derivative of an inverse function. You're going to need to commit this one to memory, so let me write it down. If f and g are inverses, and let f be a function that's differentiable on an interval I, and its inverse is called g, then g is differentiable at any x for which f prime of g of x is not equal to 0, and to find that inverse, that derivative of the inverse at x, which is the inverse function, derivative evaluated at x will be 1 divided by the derivative of f evaluated at g of x. And of course, since we're dividing, we've got to be careful and say that we can't divide by 0. Okay. So let's do an example that uses that idea as a starting point. So I've got a function, it's a cubic function. Oops. It's minus 1. There we go. So 1/4 x cubed plus x minus 1. We're asked to find the value of f inverse of x when x is 3. Okay. So if x is 3, what is f inverse of x? All right. So our function is a polynomial function, so we know it's differentiable, and we know it has an inverse. So I'm going to think of the inverse as, instead of writing g, I tend to write f inverse. And according to this last statement, f inverse, its first derivative evaluated at x, which is given to us to be 3 in this problem, will be, according to the that theorem 5.9. And again, f inverse, then this will be f of f inverse of 3. That's g of 3 in the formula. Okay. So what we're going to have to do is think about if the function of x, if its inverse is considered, even if I don't know how to find that inverse, and for that cubic function I'm not sure I'd know how to solve that, at least not necessarily. But the fact that x is 3 for the function means that, no, I'm sorry, let's look at that again. Since x is 3 for the inverse, so I wrote that a little bit incorrectly. Let me back up and write that again. Oops. Okay, since f inverse of 3 is what we need to find, then that means that that x is 3, and whatever that equals, I'll call it question mark for just a second, is a y value for the inverse function. And a y value for the inverse function becomes an x value in the function. And the x value in the inverse becomes a y value for the function. And so what I want to find out is what number would make that true. So instead of question mark, I'm going to call it, no, I'm going to leave it as question mark. So 1/4 times question mark cubed plus question mark minus 1 equals. And so 1/4 times question mark cubed plus question mark equals 4. So let's see if we can solve that for question mark. So one thing I'm going to do to make it easier is I'm going to multiply both sides by 4 so I don't have any fractions. And I'm going to, I don't think you're going to like this a whole lot, so I apologize up front. But I'm just going to start thinking of numbers, because solving a cubic equation like this, I'd have to be able to factor, and I don't want to get into the whole factoring theme with cubic functions. So I'm just going to start guessing. So what if question mark were 1? 1 cubed plus 4 times 1 is 5. Nope, that's not it. How about 2? 2 cubed is 8, plus 4 times 2 is 8. It's 8, that's it. Question mark is 2. Whew. Lucked out, got that one pretty fast. And so what that means, of course, is that this f inverse of 3, we now know that's 2. Okay, that's what we needed to find out. So what is f inverse of 3? To be able to continue this problem. So this is going to be 1 over f prime evaluated. Now it's known to be at 2. So now let's find the derivative of our function. That's going to be 3/4 x squared plus 1. And if we substitute 2 into that, which is what f prime of 2 means, that'll be 3/4 times 2 squared plus 1, which simplifies to be 1/4. Okay. An interesting thing here that's going on graphically is if I were to graph these two functions, not very perfectly. That's not my intent here, is for this to be a perfect graph. I just kind of want you to see something. So this one would go like this, let's say, and that's f. And let's then graph g. And it looks something like this. I'm sorry, f inverse. I don't know if I said g or not. I think I may have. That's f inverse. And at the point on this function, on the inverse function at 3, 2, the slope of the tangent line at that point that we just found, that slope is 1/4. That's what we just found. Then, if we were to go to the point 3, 2 on the graph of the function and look at its slope, that slope was 4, because 3. Let me see, is that correct? Oh, I know what I did wrong. I'm so sorry. I just realized what mistake I made. I used 3, 2 again, and that was the mistake. It's supposed to be 2, 3. So I apologize for that. I could not figure out what I'd done wrong there for a second, so excuse my mess up there. All right, so the corresponding point on F is 2, 3. And if I put 2 into this slope formula, 2 squared is 4, 3/4 times 4 is 3, 3 plus 1 is 4. Notice that those slopes are reciprocals of each other. At the AB switch to BA point. And that's kind of what I wanted you to see, is that the F and F inverse have reciprocal slopes at the points AB and BA. Okay. Right. That was actually parts A and B. I just realized. So let me go back here and label. This was part B over here. This answer of 2, that was the answer to part A. And 1/4 is the answer for part B. Okay. Very good. And so what we can say here is that if y, which sometimes might be called the inverse function g of x, or it might be denoted with inverse notation, but if that's what we're given, then f of y will be x, is the original function, and f prime of y will be called dx dy, because our variables have switched roles. So therefore g prime of x, which is dy dx, according to that theorem before, that's going to be 1 over f prime evaluated at g of x, which can be called, if we want to, f prime at y, because that's what g of x is equal to, according to this statement right here. which is also known as dx dy, and so that means that dy dx will be the reciprocal of dx dy. That's what this statement says. Okay, example 6. All right, next thing. Example 6. I think I've talked about this function already, so oops. If we let f of x equal x squared, but restrict ourselves to x greater than or equal to 0 so that we are one-to-one and monotonic, and let f inverse of x, as we found earlier, be the square root of x. Show that the slopes of the graphs of f and f inverse are reciprocals of each other at the following points. So the derivative of x squared, of course, is 2x. And since the square root of x can be rewritten as x to the 1/2, the inverse's derivative of x is 1/2 x to the negative 1/2. Oops. Also known as 1/2 square roots of x. Okay, so A. So at 2, 4, the slope of f is f prime of 2. 2 times 2 is 4. For the inverse, that point is at 4, 2, and the derivative of our inverse function, evaluated at 4, is 1/2 square roots of 4. Square root of 4 is 2. 2 times 2 is 4. So the answer is 1/4. And of course, 4 and 1/4 are reciprocals of each other. Okay, that one's done. And then part B, at 3, the derivative of our function at 3 is 2 times 3, which is 6. And at 9, 3, the derivative of our inverse function, evaluated at 9, is 1/2 square roots of 9. Square root of 9 is 3. 3 times 2 is 6. That's 1/6. And of course, those are reciprocals. And so that completes this section of notes. I will see you in class. Have a great day.